Alright everybody, welcome back. This is our second video related to Section 5 of Unit 3 of AP Calculus, selecting procedures for calculating derivatives. In this first example, example 1, we're going to go through and look at each of these functions and think about the rules that we would use and what order we would use them if we were finding all of these derivatives. Now, I've mentioned a couple of times in earlier videos the idea that when we're applying multiple rules, I like to think about getting myself started by thinking about how I would evaluate the function if I were to substitute a value of x in and want to find the value of the function. And kind of running through my head mentally and saying, okay, what order would I apply, different pieces of this function? And then when I get to what would be my last step, that reveals to me what is the best choice of my derivative rules to start with. So for instance, in the first one here, y equals e to the x plus 3 sine of x, if I substituted a value in here to calculate the value of y, the very last thing that I would do in that calculation is I would add the two values together from e to the x and 3 sine of x. So when I'm taking the derivative, the place I'm going to start here when I'm using my rules, I'm going to start here with the sum rule. The derivative of this expression is equal to the sum of the individual derivatives. And then I'm going to apply, I need to apply the exponential derivative rule, an exponential derivative rule, to take the derivative of e to the x. And then to take the derivative of 3 sine of x, I need the constant multiple rule to deal with the 3. So it's just going to be 3 times the derivative of sine of x. And then, of course, I need my trig rules specifically for sine of x. And those are all the derivative rules that I'm going to use in order to find the derivative of e to the x plus 3 sine of x. All right, let's go on to y equals the third root of the quantity 4 minus x squared. So I'm going to think about this, and I've talked about this on numerous occasions. I'm going to think about this as an expression raised to a power. I think about it that way anytime I have a root. So if I'm taking this, the very last thing I would do if I were calculating the value in evaluation is I would take the derivative of, I would apply this outside exponent here. So here I'm going to start with the chain rule, since this is a composite function. And then as I apply the chain rule, there are different things that need to happen in the chain rule. When I use the chain rule, I'm taking the derivative of the outside, leaving the inside the same. That's the first thing I do, and that requires me to apply the power rule to take the derivative of the outside, leaving the inside the same. And then I'm going to take the derivative of the 4 minus x squared, and in order to do that, I need the constant rule. Actually, even before the constant rule, it's hard for me to sometimes think on such fundamental levels. I need the difference rule, since we're taking the derivative of a difference of two functions. And then I need to use the constant rule. And I need to use the power rule. Okay, keep cranking here. E to the x tangent of x. So again, I'm going to start by looking at this and going, okay, I need to apply the exponential rule within the context of the chain rule. I'm going to have to apply the chain rule here, since this again is a composite function. I don't know why I numbered that step 2. Let's start with step 1 instead of step 2. Start with the chain rule, and then I'm going to take the derivative of the outside, leaving the inside the same. And the derivative of the outside function here is e, so I'm going to go with my exponential rule next, leaving the inside the same, and then I need to multiply by the derivative of the inside. So how do I find the derivative of x times tangent of x? I start with the product rule, and then I've got x times the derivative of tangent of x, so I need to use the trig rule. for tangent next. And then I need to take the tangent of x times the derivative of x. And in order to do that, I need to use a power rule for the derivative of x. All right. In this choice, I think I would like to think about this as 3 times x to the negative 4th. If I think about it that way, let's see, I need to use a constant multiple rule first. And then the power rule. First one in a while where I didn't have any composite functions, so I didn't need to use the chain rule. And in the next example, we're right back on the chain rule. We've got a composite function, natural log of the quantity 5x squared plus 1. So the first thing I'm thinking is chain rule. And applying the chain rule means I take the derivative of the outside, leaving the inside the same, the derivative of natural log. So we've got the logarithmic rule. Derivative of the outside, leaving the inside the same. And then I take the derivative of the inside, the derivative of 5x squared plus 1. So I'm using the sum rule to take the derivative of that. And then I'm using the constant multiple rule for the 5. The power rule for the x squared. And the constant rule for the 1. Okay, now for those of you who are watching along out there, if you want to do the last half of the ones from this list, you can go ahead and do that. You can pause now, and through the magic of video making, and when you come back, I'll set it at about the 7:25 mark. When you come back, all the answers will be up here. So go ahead and pause real quick, and then magic. All right, we're back, and through the magic of video, you can see my answers for the remaining questions on that list. Go ahead and take a look at those, and you can pause again now that the answers are revealed if you want to see if you can come up with the way that I, decided that these were the rules I was applying and in that order. We're going to continue on and do some more examples. All right, example 2. If f of x equals x squared plus 2x, then the derivative with respect to x of the quantity f natural logarithm of x is what? So looking at this expression that we're taking the derivative of f of log of x, that's a composite function. So that tells me apply the chain rule first. So I'm going to take the derivative of the outside, leaving the inside the same, times the derivative of the inside. The derivative of natural log is 1 over x. Okay, and now I have a couple of different choices. I think my best approach is just going to be to find f prime of x and then substitute in the natural logarithm in order to represent this piece right here of my derivative. So I'm going to go ahead and take the derivative of f. That's f prime of x is equal to 2x plus 2, and then I'll substitute natural log in there. So that gives me the quantity 2 times natural log of x plus 2 times 1 over x. And let's see, it looks like that is going to be answer choice A. All right, next example. If y equals the arctangent of e to the 2x, then dy dx equals what? Okay, so again, we're going to have to apply the chain rule in taking the derivative of this. So we're going to start with the outside function, the arctangent. The derivative of the arctangent is 1 over 1 plus whatever is inside squared. And then applying the chain rule, I'm going to multiply that times the derivative of the inside. The derivative of e to the 2x is e to the 2x, again, another chain rule application, derivative of the outside leaving the inside the same, times the derivative of the inside. The derivative of 2x is 2. And so simplifying all of this, we end up with 2e to the 2x over 1 plus e to the 4x, it looks like. Let's see if I can find that somewhere. It looks like that is answer choice B. All right. Up next, example 4. Let's take a look at what example 4 looks like. If f of x is equal to sine squared of the quantity 3 minus x, then f prime of 0 is equal to what? I frequently recommend that when you have sine or any trig function raised to a power like this, that even if you don't rewrite it, you make sure you think about it as sine of the quantity 3 minus x raised to the second power, so that we can keep our chain rule applications in order here. So again, I'm going to have to apply the chain rule to take the derivative of this. F prime of x is equal to derivative of the outside, leaving the inside the same. The outside function is raising to a power, so I'm going to bring that power in front and drop it by 1 power. That's my derivative of the outside, leaving the inside the same. And then I need to take the derivative of the inside, the derivative of the sine of 3 minus x, which again is a composite function. And so it's going to require a second application of the chain rule. So I'm going to take the derivative of the outside, derivative of sine, leaving the inside the same, times the derivative of the inside, the derivative of 3 minus x, which is just negative 1. And so f prime of x is equal to negative 2 sine of the quantity 3 minus x to the first, cosine of the quantity 3 minus x. If I evaluate this at 0, it's going to give me negative 2 sine of 3, cosine of 3. And so B is our answer choice. And one last example here, example 5. If natural log of the quantity 2x plus y is equal to x plus 1, then dy dx is equal to what? So we've got some implicit differentiation going on here. This should be fun. So the left-hand side, I'm going to apply the chain rule because I have a composite function. So I got 1 over what's inside, because that's the way the natural log works, times the derivative of the inside, which is 2 plus dy dx, is equal to, and the derivative of x plus 1 is just going to be 1. I think the easiest way for me to solve for dy dx here is just going to be to multiply both sides by the reciprocal of this piece in order to get what's inside the parentheses here by itself. So I multiply by 2x plus y. 2x plus y times 1 gives me 2x plus y. And then to get dy dx by itself, I'm just going to go ahead and subtract 2. And it looks like B is our answer. Alright folks, that is it for this video, and that is it for section 5 of Unit 3 of AP Calculus. We'll see you next time. Have a great rest of your day.